All right, so what we have for today is 3.7 rates of change. And if you remember from your prior math knowledge, rate of change is also sometimes known as slope, where we calculate it by looking for the change in y over the change in x. And if you can think about that concept, that's pretty much what we're going to be doing today. Okay, first example. When a rock is dropped from a high place, the distance the rock travels, ignoring the wind, is given by this formula. D of t, distance is a function of t, which is time, 16 t squared. T represents time. D of t, that's a t, represents distance. And this example is going to be in feet after t time, which is going to be seconds. Okay, so they give us some data. T stands for time in seconds, and this is really our independent variable, so we're going to label it x. D of t, which we used to see as f of x, we're going to label as y, and this is our distance in feet. Okay, so we need to calculate the distance the rock falls between 1 seconds to 3 seconds. So basically what we're looking for is the function or the y value after 3 seconds and the function after 1 second to see how far it fell during that time frame. Well, if you look at your chart, d of 3, t would be 3, would be 144 feet. Distance after 1 second, we were only at 16 feet. So we take the difference between the two and we figure out that that rock traveled 128 feet. So all we're doing here is taking our distance among our y values. All right, average rate of speed. Normally when we think of rate of speed, we think miles per hour. But in this example, we're looking at feet per second. And most often, the time ends up on the bottom. And go back to your change in y over change in x. Most often, the time is represented by the change in your x value. Okay, so basically what we're looking for here is distance over time. High level, just to get used to the format, you find distance of your second value, and we're going to let actually b represent that. Just a variable for any of those time values. We're going to subtract our starting point, distance after a, and in the denominator will be our change in those two values, b minus a. So it's kind of like, or it isn't like, a and b are our x values. We're taking the difference in our y values and we're dividing by the distance in our difference in our x values. Another way to think of this is the change in f of x divided by the change in x. All of these represent the same thing going on. It's just different ways of looking at it. Okay, so let's look at some real examples here. Example number 1, rate of change for the falling rock. Find the average rate of speed over a given interval. They want us to go from 1 second to 4 seconds. So to make it a little bit easier, I'm going to actually figure out what the ordered pairs are. Since the time represents x, go back to your chart, find where x is 1 and the y value is 16. Find where x is 4 and the y value is 256. Okay, now when we set it up in our formula, change in y over change in x, we want to take the larger y value first, subtract the original y value, divide it by the corresponding x value minus the corresponding y value. So it's really important if you start with 256 on the top, you start with 4 on the bottom. There's always implied parentheses here, so if you're putting it into your calculator, make sure you're using your parentheses in the right spot. This is a pretty easy one to mental math. 256 minus 16, 240. 4 minus 1 is 3. By now, 80 should be popping off the page at you. And the distance we traveled, given as a rate of change or an average rate of speed, is feet per second. And that's your answer. We're going to do the exact same thing one more time. Again, our x values are 2 and 4.5. So at 2 seconds, what's our y value? 64. And then at 4.5 seconds, what's our y value? 324. You plug and chug. Again, implied parentheses. You get your final answer of 104 feet per second. Okay, next example, rate of change in volume. Now your volume formula is a little different, and we're looking for the volume of a balloon. And I'm not sure how many of you would remember volume back in the day of a sphere, something like the radius cubed divided by 55, if that sounds familiar. We're going to rewrite that so it's a little bit more in function notation. And we'll say v of x equals x to the third over 55, and x is going to represent our radius. So here's what we need to find first. Find the average rate of change. How much is the volume growing if the radius increases from 5 to 10? Radius is our x value, that's our independent value. As this radius increases, our volume will also increase. What we need to find first is the volume at 10, subtract the volume at 5, and divide that by 10 minus 5 on the bottom. Now what's going to come out with a complex fraction, so we're going to have in our numerator 10 to the third divided by 55, and we plug it in. 5 to the third divided by 55, parentheses, all over 5. Okay, when you plug it into the calculator, make sure you use your parentheses, otherwise the math is not going to go well. 10 to the third divided by 55 minus 5 to the third divided by 55 should give you 15.0909 divided by 5. Last step, go ahead and round it to 2 decimal places. And we should have just figured out that this balloon will grow at a rate of 3.18. I believe it's going to be gallons per inch. Yeah, here it says volume is gallons, radius is in inches. Okay, next one. I guess we should finish it off. You can say that for every inch the radius increases, the volume increases by 3.18 gallons on average. Okay. Next page, example number 3, rates of change in manufacturing costs. This is one for the calculator. And what we'll do to figure out our x and our y values is we'll use the table function. Okay. Also, when you go to graph it, you're going to see the window is pretty messed up. So what I want you to do is adjust your window. So when you plug it in, you get a graph that looks like this. You should know by now x to the third gives you a little more than that just going on. So to get a great window, and since you're talking about manufacturing costs, you are primarily dealing with the first quadrant, where along the x value, your manufacturing desks, this is the number of your desks, and along the y-axis, this is going to be your cost. Pretty typical graph in economics and accounting, has lots of real-world applications. But to get this window right, what I want you to do is put in your x min at 0, your x max at 50, your y min at 0, and your y max at 50. Okay. You can leave your scale at 1. All right, because what you kind of want to do is minimize costs to produce these desks at all possible. Okay, so once you've got a pretty graph, go to your table. Hopefully you're going up in increments by 1. If you are not, you can go second window or second table set, and right here, change table. Make sure that's set to 1. And then all your values on your table for X will go up by units of 1, no decimals. Okay, so here's what we need to do. We want to compute the rate of change for the cost as we go from 0 to 10 desks, and then again from 10 to 30 desks, and then again from 30 to 50 desks. So from 0 to 10, I want to find the cost after 10 and the cost after 0, and I want to divide that by the change in the number of desks, so 10 minus 0. On my table, it tells me that to produce 10 desks, my cost is 15.9. To produce 0 desks, you would think it would be 0, but it's not, because you've got some fixed costs that you can't avoid. So that would be 5. And on the bottom, we're just going to divide by 10. Again, in your calculator, remember you've got implied parentheses around your numerator. So 15.9 minus 5, close your parentheses, divide by your denominator, and you should get cost to produce these desks is 109 per desk. Since the slope of this line is ever changing, it may go up, it may go down. I'm assuming in here the costs will go down a little bit because it's a little flatter, and then I'm assuming the costs are going to shoot up again. Law of diminishing returns, where you invest a little too much and it's going to cost you too much to produce them. So let's go 10 to 30. C of 30 minus C of 10, denominator 30 minus 10. Back to your table, grab those values. And you should get 23.3 minus C of 10, which we just had a second ago, all over 20. Plug and chug, and you should get something quite a bit different. Again, don't forget your parentheses. Don't forget you can pause the video at any time. Holy cow, and look at the decrease. 0.37 cents per desk. Now this is in thousands, so we'd be adding 3 zeros or moving our decimal places 3. So you can see right here, good deal to produce the desks. Here, not so much. And it would be curious to see what you get for this answer, but try that one on your own. All right, last thing we have to attempt today. Looking at the graph, seeing if we can compute a rate of change. Okay, maybe not too bad. What they gave us here is temperatures at different times throughout the day. They used military time, but in the example here, they're saying 4 to noon, and then they say 3 p.m. to 8 p.m. So maybe we want to change the 16 to 4 p.m., the 20 to 8 p.m., and then the 24 would be midnight. Okay, so how are we going to get these values? Well, my X value is time, so at 4 a.m., my Y value looks like it's about 40 degrees. And then at noon, my Y value looks like, oh, it's right under 60. So let's say at 12, my Y value is 58 degrees. Once you have it in this form, pretty easy to compute your rate of change. 58 minus 40 over 12 minus 4. I believe it looks like a temperature change. Pause it if you don't want to know the answer just yet. Of 2.25 degrees per hour. And for the next one, from 3 to 8, let's list an ordered pair. So at 3 p.m., I'm actually just a little bit farther in. then 4 o'clock. I'm going to say about 68. And at 8 p.m., it looks like we're pretty on maybe a little bit over 52. Let's say 53. Now, if you're off just a little bit on these slopes, don't worry about that too much. So now let's go with 53 minus 68 over 8 minus 3. So I believe I get negative 15 divided by 5 simplifies to negative 3. And again, you're talking about degrees per hour. And does that rate of change make sense? I think it does, because I think I have something that looks like a little bit of a negative slope here. And we can circle our answers. Okay, so that's about it. Problems, don't worry about this right here, because we just talked about it here with the negative slope. Problems you should try for homework. Page 220. These are kind of confusing. 1, A and C. 2, ACD. 3, 4, 5, ACEG. 8, 9, 11, and 13. Let me switch them up just a little. So page 220, 1, only A and C. 2, ACD. 3, 4, 5, A, C, E, G, 8, 9, 11, and 13. Good luck.